Welcome to our final session for today, which is looking at using Autodesk CFD for predicting the thermal performance of products and improving the thermal performance of products. So, by way of an introduction, my name is David Hick, and I lead our technical team for simulation at Autodesk across Europe, Middle East, Africa, and India. And it's a huge pleasure to be here this afternoon. By way of a brief agenda, I've shortened the presentation to around about 30 minutes because I know we're running over time today. So I'm going to kick off by just reminding us why customers perform simulation, and then talk specifically about Autodesk CFD for simulation. And then I'll provide you with a quick video demonstration of how Autodesk CFD can be used for determining the thermal performance of electronics products. And then we'll work through some customer examples. So it should be a fairly brief session. So to start with, why are engineers performing simulation? It can come down to a number of key reasons. So engineers are performing simulation to test their products before they're built, before they're manufactured, to identify if there could be any problems and try and resolve those problems early. Secondly, simulation is used to help optimize designs. Obviously, there can be many different trade-offs, for example, strength and weight, or if we're looking at thermal performance of products, it can be, for example, improved ventilation versus cost. And then finally, reducing the reliance on physical testing. Physical testing is time-consuming, it's expensive, and it provides limited information. But the main reasons why our customers are performing simulation is really because the products that they're developing are demanding greater performance, quality, reliability, and at the same time, there's increasing pressures in terms of reducing cost and competitive separation. Now, what we're seeing in terms of the electronics industry are trends towards products which are becoming more compact and have increased technology. So, if I look at my kitchen at home, I have a toaster which has a microchip in it, and I have a heating and ventilation system in my house that's connected to my phone. So all this technology, as great as it is, comes at a price, and that is that often it involves featuring components which do get very hot and require cooling. So, some typical considerations during cooling design. So first of all, as an engineer, we need to understand which temperatures the product can work to, which are acceptable. Secondly, the size of the product. So there will be limitations in terms of the kind of space claim of the product. And of course, if we make the product too small, perhaps that impinges on some of the components. There could be issues with product failure because of conduction of heat to the surrounding enclosure. Noise is a consideration, so if we're incorporating fans, obviously fans generate noise, so it's not particularly useful if the product we're developing is a stereo system for use at the home. Airflow, we have to consider how the product is ventilated, where the air is going to come in and out of the product, and trying to avoid recirculating warm air back into the system. Cost as well, so as we look at developing different design alternatives, we need to look at which one is the most cost effective. As we start to introduce components to improve cooling, they do come at a price. And of course, the environment in which the product's going to work in, is there the potential for there to be dirt or dust to be drawn into the system that could damage the performance of the products? So these are all considerations that we have to think about as engineers, and of course, there are different approaches that we can take to dealing with these challenges. So oftentimes with products, the key is really looking at how to ventilate the product, how to allow cool air to enter the product and the warm, stale air to exit cleanly without being recirculated. At the same time, perhaps we can't rely on natural convection. We might have to use fans to drive airflow through the product. So where are those fans located? How many fans should we use? What size of the fans should we use? And how is the product laid out? So it can be with some products, the design of the board really limits the packaging envelope for the product, but these things are connected together. And of course, the use of heat sinks, the size of the heat sink, the material of the heat sink. Are there alternatives to using heat sinks like thermoelectric coolers for dissipating heat from the product? So let me give you an example of a real-world situation where a well-known company failed because they hadn't looked at using simulation early in the design process. So what we're seeing here is an example of a gaming system from Microsoft. So we're probably all familiar with the Xbox. So globally, I think around 60 million products have been sold worldwide. But when it was first introduced to the market, there were serious product failures. In fact, 42% of customers had a failure which required Microsoft to repair or replace that product. So out of 60 million products, that's a lot of field failures. Now, Microsoft did a very good job of replacing the customer's products, but of course, many of those customers that got a second console, they experienced failures as well. So around 23% of customers had a second product which failed, and then Microsoft sent them a third product. And of those customers that had 3 products sent to them, 13% failed. So you can see the statistics here. And right at the end, you've got somebody who's a very loyal Microsoft customer that's actually received 5 boxes and they all failed. That's quite impressive statistics. Now, at the same time, Sony produced their product and Nintendo produced the Wii, and Sony had failure rates of around about 8%, and with Nintendo, it was just 1%. So the issue here was really, it wasn't just cost, it was affecting Microsoft's reputation. So what they could have done is they could have looked at the design of the Xbox earlier by performing a simulation. So they could have simulated how the product would have behaved in different environments. What they'd overlooked is the fact that on a test bench, surrounded by open air, the product works very well. But in reality, many customers place the unit inside a cupboard or a cabinet, along with a video recorder or DVD player. And that was the issue. So air coming out of the back of the product was re-ingested back into the design, and that was what was causing the failures. So they could have predicted this. So through the use of simulation, they could have measured temperatures for the devices that were failing. They could have identified the reason why those devices were failing. And then based on these results, they could have made some better decisions about improving the design. So they could have simulated a number of different design alternatives. So here we have the original design, a second design where the ventilation has been moved slightly, a third design which incorporates an enclosure to guide the airflow over the heatsink, and then there was another design where they looked at a different design of heatsink. So it was actually the third design that helped resolve the issues. So by using simulation, it's not just providing information about temperatures or yes or no answers. It's providing a lot of insight in terms of how the product works. So when is the best time to perform a simulation? So if we look at a product development process going from conceptual design through to testing and through to manufacture, and then putting the products into the market, what we know is that the ability to make changes to that design, which can make it work better, reduce over time because the costs increase. So if we put a product into the market like the Xbox, it's very expensive to make a change because it's a product recall. But if it's earlier in the design process, if it's at the conceptual stage, it's very cheap. We can look at many, many different alternatives and many different concepts. So in speaking with our customers, what we know is that many of them perform physical tests. So they're creating a prototype and they're measuring the temperatures of the products. And on average, what we know is that manufacturing companies produce approximately 10 prototypes per new design that they're developing. Now, as they're testing, if they find the product is still not working, then they perform more prototypes, more testing. The product can go to market late, and it can be very expensive. If they do not perform enough tests, then the product could go to market, and there could be quality, performance, and reliability issues. So we're encouraging our customers to take a different approach and use simulation as a way of virtually testing their products. And they can do this very, very early in the design process when they have the time, when it costs less money. And they can investigate different designs, different conditions, different environments for the products. And what that means is that when they get to manufacture, they have more confidence that the product is going to work correctly. So the key thing here with simulation is making better decisions sooner. The earlier simulation is used, the bigger the benefits. So specifically for Autodesk CFD, now you may not know, Autodesk is often associated as being the AutoCAD company. Very few people are aware that we actually have a very extensive portfolio of simulation products. So over the last 12 years, we've been acquiring technologies and companies. In fact, we spent almost $500 million on acquiring simulation companies to build up a portfolio which is much bigger than ANSYS. Back in 2011, we acquired a company called Blue Ridge Numerics that produced a product called CF Design. And CF Design was a tool that had been developed since 1992 for engineers to use with a CAD system to understand the flow and temperature performance of their products. So that's the product that's now become Autodesk CFD. The reason I tell you this is it's not new software. It's something that's been in the market for over 20 years. It's well established, it's credible, and it's a reliable product. So what does CFD stand for? The joke here is that CFD stands for Colors for Designers, which is partly true because when we look at the results of an analysis, we see some beautiful colors from blue to red. Red often means bad and blue means it's okay. And this is a way of kind of identifying maybe how temperatures change in the model or how the airspeed changes in the model. But the point is, someone who's not a CFD specialist like me can look at the results and understand what it means. If we look at these images here, for example, the one in the middle, this is almost like a thermal camera view, and it shows areas in white which are very, very hot, and then the darker areas are obviously indicating areas of the model which are much, much cooler. So visually, I can quickly see where there could be some potential problems. So in a way, it is colors for designers, but CFD actually stands for Computational Fluid Dynamics, and it's looking at liquids and gases, but also the effects of temperature. So CFD is a very quick way to use your computer as a test bench. So we can set up a simulation that represents a real-life physical test and find that the results are very comparable to what we see physically. But it's much, much more than that because we get a full picture of how the heat moves through our products. We can work out where the heat moves to and how, whether it's through conducting, convecting, through radiation. We can also get a very clear picture of why the heat is at a certain temperature, and that's often down to airflow. If we channel more airflow over hot components, we make them cooler. So heat and airflow are connected together. So being able to visualize this is very, very important. So this way, as an engineer, if we can identify problems very early and get some guidance on how to improve the design, this is hugely valuable. And it doesn't need to be something that's driven by a specialist. So through the use of CFD, it's possible to visualize how the air moves, how the airflow covers a product, or how it's balanced inside a product. We can look at the temperatures, we can look at the performance of a fan, if we're including one, and we can look at the effect of different ventilation strategies, how efficient the airflow is at entering the products and leaving the products. And finally, if we're using heat sinks to remove heat, we can see how effective that heat sink is. Maybe the heat sink needs to be redesigned or relocated. So CFD is being used at many different levels. I think you can look at this at different levels in the supply chain. So we have customers who are designing individual components or products, such as computer chips or fans for cooling. We have customers that are working at a board level. So what they want to do is they want to look at how the heat is conducted through the board and the effect of the choice of location of components. Thirdly, at a system level, so this is where we start to see fans, enclosures, ventilation starting to play a role. So in this case, often the engineers are working with equipment that they can't change, but they can control the packaging and the ventilation. And then finally, all the way up to room level. So 4% of the world's energy, 4% is consumed in data centers. That's a lot of energy. So efficient strategies for cooling these rooms can lead to some significant cost savings. So we've got customers working at every single level in that chain. So I'm going to start with a demonstration for you. And before I do, one of the kind of key challenges, I think, for engineers is that they're often working with ECAD data, electronic data, that often has a lot of detail. So, you know, this detail can be simulated, but often it's unnecessary. It doesn't add any additional accuracy to the simulation. So through the use of a product called Sim Studio Tools, which comes with our simulation software, or through Fusion, it's possible for the engineer to simplify all of these details. So they can effectively select the entire model and specify fillets, rounds, small details, small protrusions or extrusions in the geometry below a certain size and eliminate all this detail. So if these components are not adding anything significant in terms of heat, or they're not containing the flow, the airflow, they can go. They're not required. And we focus then on the key components inside that model. So here you can see with this example, many of these smaller devices are going to go with just one mouse click, heavily simplified down, and that's now ready for a simulation. So let's take a look at the simulation example. And hopefully that's going to play. Whoop. I have to go back. It should be this one. There we go, thank you. So, here's a nice example for you. This is a graphics accelerator card, and
directed efficiently.
That's
the interaction of these.
I think you can lose the audio.
Impact on product performance and
that's it.
How
we'll switch it off. Thank you. So what we have here, this is actually a real product for NVIDIA. So we've got a graphics processor, which is the hottest part of the assembly, and that is mounted on the board. On top of the chip is a heatsink. The heatsink is then covered by a plastic casing with a fan. So the fan is driving airflow over the heatsink to try and cool it. We're going to look at a number of different designs. So we're going to start with an original design here with these straight fins for the heatsink. Then we have a second design where we've made a cut into the heatsink to see what effect that has on the airflow and the temperatures. And then finally, we've got a third design where we're going to look at a different heatsink profile, which is tapered, to see what benefits that could bring. So we take the data, the geometry, straight from the CAD, and it can be any CAD system. It could be Inventor, SolidWorks, Fusion, Pro Engineer, it could be CATIA, in any file format, straight into the CFD interface. And we can set up and solve a simulation using the real-world heat loads and the real materials coming from the CAD system. And here we can visualize areas in the model where we've got higher temperatures. So you can see on this thermal imaging scale, areas in white are indicating the hottest temperatures in the model, which is where that device is located. Now, to understand this better, what we then do is we look at airflow. So we're seeing a cross-section through the model, and we're visualizing airspeed. Areas which are slower are in blue, and these faster areas are in red. And we can see that there's a variation in the speed in which the air is moving through the heatsink. That's the reason why we've got areas where it's hotter. Now, another way to look at this is by looking at the flow direction. And what we're actually seeing is all the airflow coming off the fan, where it's moving very fast, but it's not going between the fins of the heatsink. It's effectively, it's choked. It can't travel. It's too close. So that's where we have a problem. Now, there's many different tools for visualizing this. So one example is what's called an ISO volume. So this shows us areas of the model where the air is traveling at a certain speed, and it gives us a sense of the airflow balance. So the airflow here is all traveling at the same speed, but there's a gap in the middle, and that's indicating it's stagnant. It's a dead zone where there's no airflow. That's the reason why we have the high temperatures. So we're getting information that we wouldn't get from a physical test alone. But not only that, it's possible to then compare the effects of different designs. So we can see the design on the right allows more airflow between the fins of the heatsink. It's a much more efficient design. Not only that, it's going to be lighter as well, uses less material. And then we can take a look at the temperatures, and we can see that the temperatures are lower as well by using the modified heatsink. So the software provides a very easy way for engineers to make side-by-side comparisons on 2, 3, 4, 5 different designs. What we're now going to do is we're going to create a graph. We're going to plot how the temperature and the velocity vary all the way across the heatsink. So here we can see the graph, and it updates for both designs. And we can see very clearly that design 2 has a much more uniform airflow. And then if we look at temperatures, design 2 has much lower overall temperatures. So it's definitely the best design from these two. So as well as comparing visually, we can actually measure the chip temperature. So here we can measure what's called the junction temperature of the graphical processor chip. And we can see very clearly the difference between the 3 designs. Design 2 is the only one which is acceptable. That's below the criteria. So the product that we have is not the only simulation tool that's available in the market. But there's a perception that simulation is something that is difficult to use, it's expensive, and it requires dedicated hardware. And that perception exists because it's true. There's a lot of simulation products which are difficult to use. They are expensive to buy and to run and to maintain, and they do require expensive hardware. So we're trying to take a different approach to this and enable simulation to be more accessible to a broader audience. So first of all, in terms of ease of use, our users are engineers. So the best person to drive the software is somebody who drives the CAD system, because that's the person who would make changes to the design to make it better. There's no point having somebody at the end of the process performing the simulation if they're not connected to the initial design or they're not driving the CAD system. So the majority of our users are in fact engineers that would be running other tasks. They might be testing products, developing new designs, but they're not specialists. And secondly, in terms of hardware and cost, the software works on any laptop. So any hardware that's capable of driving the CAD system is appropriate for driving our CFD. But not only that, it's scalable onto the cloud. So if we're running an analysis on the desktop, it's a sequential process. It's one analysis after another. But if we run the analyses on the cloud, all analyses can be solved simultaneously. So the analysis that I showed you, that took about 6 hours to run the 3 different examples that we saw. By running on the cloud, it takes just 30 minutes. Not only that, this week we've made a significant change to our products because we've introduced what's called Cloud Premium at Autodesk. This is exactly what Callan was talking about this morning. So what this is the ability to use 256 cores in the cloud on any specific analysis. So that's rather like having 256 computers connected together, solving just one problem. So now it's possible to run this entire study in less than 3 minutes. So this is something that just occurred this week. It's now available to all our subscription customers. There's no other company on the planet that has a cloud service that's scalable in this way. We're the only company offering it. So what Callan was showing you this morning is live and it's real and it exists right now today. So a few quick sample applications for you where our customers have been using the product. So this is a very simple example of a modem, a router device used in the home. And the problem here was quite simple. It's just overheating of one of the key devices. Their initial measurements were showing that the product was getting to around about 63 degrees. And so what they thought they needed to do was put a fan. This is always a kind of common solution. Let's just stick a fan on it and make this product cooler. So they made the enclosure bigger, and they put on a fan, and yeah, the temperatures came down, but it comes down at a cost. There's more components, there's more weights, and obviously the fan requires energy. What they didn't realize, though, is there was a much better strategy. So instead of relying on a fan to take the heat away, how about making a better conductive path between all the components? So by simulating the design, what they found is they can come up with a more optimum solution that actually removes the heatsink completely because they chose materials which are more conductive. Yes, they still have the fan, but they save significant weight by not having the heatsink. Another simple example, we've all got memory sticks or USB drives. There's some simple requirements with these products, and one of them is the touch temperature. So these things can get very hot when they're charging or receiving, transmitting data. So for this company, what they tended to use were thermal pads. These are a kind of sponge-like material that you can put over components and connect it to a casing. And it's a way that heat can be conducted to an enclosure. Now, the problem with that is that it was transmitting too much heat to the enclosure, and that's why it was getting very hot for the user. So there were some issues with the design. So again, what they found is that they could change some of the internal components to improve their conductivity, and that actually distributed the heat more uniformly through the products, and they didn't need to have these pads. So it actually removed the number of components, and it lowered the temperature in the product. Another example, this is not a recent one, is one of our customers in Scandinavia. You probably might recognize by the design who that is. And this is a company that's very heavy in terms of aesthetics of the design of their consumer products. And they're very desirable, and they're very, very expensive. And the product that we were looking at here is a speaker system. So this is a home speaker system with a lot of technology. It actually senses the materials of its surrounding environment and controls where the sound is directed. So some quite clever technology inside it. But it also generates quite a lot of heat. This is a 2.5 kilowatt speaker system. 200 watts is generated as heat, and that heat has to go somewhere. Now, of course, because it's a speaker system, it's not very good for it to have fans. So we don't want fans running, making a noise while somebody's listening to music. So it has to rely on natural convection. So the guys at the company went through a lot of physical testing, trying to find ways to channel this excess heat as much as possible. And they failed. They couldn't find a solution. So they used Autodesk CFD because it captured the geometry easily. And these products are not simple shapes. They're very organic shapes. And so they're able to capture the geometry accurately and run a simulation and understand that the best way to manage the heat was to incorporate at the back of the product a very thin heat sink, which is very discrete. And they could then conduct to that heat sink the heat from the chips on the board, and therefore lower the temperatures to an acceptable level. Our next example is a motor generator. So a product that we see quite a lot. So not so much electronics, but more mechanical electrics in terms of mechanical electrical cooling. And with these kind of products, there are significant challenges in terms of keeping them cool. And the example I have for you is actually from one of our, hopefully that should play. There we go. So this is one of our customers in the Formula One industry. So this is a company that's building Formula One cars, but they also provide technology for road car manufacturers. And this system is what's called a KERS system. It's a kinetic energy recovery system. So as the driver is driving the car, he presses on the brakes. That brake energy is stored inside a flywheel, and then it's released at a later date to give the driver extra power for overtaking. So that's where it's being used in the race car. Now, this product gets very, very hot. So what you're seeing is a cross-section through the design where we have the actual generator, and this is basically an iron web, which around you have copper coils for collecting the energy. Now, the problem with this is that's a huge amount of heat that's going into these webs of the core. And so this is actually liquid cooled. So we're mixing water with electricity, which I'm sure is not a good combination. But we have water that's actually going through this cooling channel here to try and cool these windings. And to prototype this product, because it's made of carbon fiber, it's very expensive, it's used in a racing car, one of these products costs over $10,000 for a prototype. It's a lot of money, and then to test it, and it's tested to failure, is hugely expensive. So they wanted to find a more cost-effective way of testing their products, especially as they build these for many different car manufacturers. So this example was actually for a Porsche road car. And so what they found is that the heat was being trapped in this area here, and so the results of the analysis led them to understand that they needed to add this secondary cooling path here, much closer to the windings. And what they found from that is that provided a more uniform temperature across the windings and lowered the maximum temperatures as well. That's just in one iteration of the design. So in summary, Autodesk CFD is a product that's built for the non-specialist. So again, our users are people that are engineers, multitasking engineers and designers who understand how the product is tested and are able to drive the CAD system. And with just 2 days of training, someone who has no previous simulation experience can start to get the results that we're seeing here. Secondly, it's integrated with all the major CAD systems. So if you make a design change in the CAD system, that modified geometry will automatically update your simulation model. So you're not having to create the simulation again from the beginning. And that works not just with Inventor, but it works with Fusion, ProEngineer, SolidWorks, and CATIA as well. It's automated, so as an engineer, I'm not having to import geometry or repair geometry or create meshes. All of those steps are automated and taken care of for me. And it's flexible in terms of its licensing. So it's a network license offering on subscription, but it provides solving both locally and in the cloud. Now, there's a broad range of capabilities. I've not gone into all of them, but it's possible to connect the CFD solution with Nastran InCAD. And Nastran InCAD is a product that's now available part of the product design and manufacturing collection. It's now free within that collection. What that will enable you to do is you can look at the temperature results of the analysis and import that into Nastran InCAD. Nastran InCAD will see that and then calculate for you how the product deforms or how the stress is increased based on those temperature variations. So it's a kind of a closed loop solution. Then visualization. So there's connections with all the Autodesk products, including Vault, but also with VRED. We used to have a connection with Showcase, but now it's with VRED, so it's possible to create photorealistic images and videos for marketing purposes. So we actually have many customers buying the software purely for their marketing departments, so they can show their clients that they have the technology in-house to solve their clients' problems. And above all else, it's fast. There's no benefit in simulation if it takes a longer time than physical testing. So now that we have not just the cloud, but cloud premium, it's possible to take any model and simulate every possible real-world test condition with different types of materials, with different design alternatives in minutes. And that way, it's really about removing risk from the design process. So as an engineer, you're going to manufacture feeling a lot more confident that design's going to work correctly the first time. Okay, so that brings to a close my presentation for this afternoon. Are there any questions at all? Everybody's finished for the day. Yeah, sure. Oh, we are finished for today. We are finished for today. So I appreciate your time this afternoon. Thank you very much for coming to Autodesk University. I hope it's been of interest to all of you, and look forward to seeing you all again next year. But I think now the hospitality is open for you. Thank you once again.